Hello, welcome to today's webinar. We're going to be getting started in just a minute here. While folks are getting logged in, I'd love to tell you about some upcoming webinars that we have over the next month or so. On Wednesday, August 17th, we're going to have a free webinar on simple rules for preventing back injuries at work and improving productivity. And that will be with Robert Fallon, PhD, CIH, AIHA, and the Southwest Center for Occupational and Environmental Health. On Wednesday, September 7th, we're going to have a free webinar on environmental epigenetics and intergenerational equity. And that will be with Mark A. Rothstein, JD. Our next industrial hygiene webinar is going to be on Tuesday, September 13th, and that'll be on understanding COVID-19 among industrial livestock operation workers, salivary biomarkers, and mixed method approaches with Carolyn Gigot, AB, and the Johns Hopkins Education and Research Center for Occupational Safety and Health. To learn more about these upcoming webinars, you can visit us online at cueh@berkeley.edu/about-CE. And without further ado, it is my pleasure to welcome you to the Education and Research Center Industrial Hygiene webinar series. This collaborative effort is on behalf of each Education and Research Center continuing education program throughout the country and aspires to provide access to research supported through NIOSH ERC programs. Thanks so much for joining us. Today's webinar, Investigating Air Changes per Hour, Outside Air, MERV, and HEPA, Does It Add Up?, is brought to you by David Moore, MPH, CIH, and the Northern California Education and Research Center for Occupational and Environmental Health. A few housekeeping items before we get started. You're going to be muted during this presentation. If you would like to ask a question, please enter it into the online chat or Q&A box. We'll save time at the end of the presentation to address as many questions as possible. This presentation is being recorded and will be made available on the Center for Occupational and Environmental Health YouTube page. And all participants who've logged in with their live registration email for the full live presentation today will receive an email tomorrow with a link to the evaluation form that will qualify you for a certificate of completion worth 1 continuing education contact hour. Once the evaluation is completed, you'll be able to access and print your certificate. And it's my pleasure to welcome our presenter for today, David Moore, MPH, CIH. David is a certified industrial hygienist and graduate of UC Berkeley's Public Health Master's Program. He's one dissertation away from a doctorate in public health. He and his life partner began Intrinsic Environment, Health and Safety in 2017, providing scientifically grounded solutions for local businesses, universities, government entities, nonprofits, to address some of society's pressing occupational and environmental health challenges. Thank you so much for joining us today. We're looking forward to your presentation.
Thanks, Michelle. Welcome, everyone. Thank you so much for taking time out of your lunch. Hopefully you're able to tuck into something delicious over the course of the hour. Generally like to keep this as interactive as possible, but we've got, I think, over 150 people, so maybe more challenging. But if there's something where you're like, oh, I really need this question answered, Michelle's going to do her best to monitor the chat so we can get questions answered in real time, but I'll try to leave time towards the end as well. All right, so without further ado, we're going to just launch right in. Probably all saw this earlier in the year, and many of you, like me, were thinking it's about time. But with climate change continuing to rear its ugly head, even though we have now an incredible bit of legislation that was recently passed, we're still going to need to contend with, well, if we ventilate spaces more, we're going to be using more energy. And so we need to be smart about it, right? We can't just over-ventilate all of our spaces, whether it's COVID-19 or some other aerosol transmissible disease, another variant, or wildfire smoke, right? It can pertain to ventilation is protective for all of these things. And I know what you're thinking. This guy again, still talking about COVID. Doesn't he do anything else? Well, as a matter of fact, I do. Was recently doing a biosafety inspection with a couple other colleagues, doing some formaldehyde exposure monitoring, and then also got a chance to visit one of the ports here in California. So as those of you who are also industrial hygienists or know about our profession, we do a wide variety of different things, which is what makes this profession so awesome. But with that said, this is something that is a particular passion for me. So my hope by the end is we're going to be able to describe what an air change is, some of the general ASHRAE guidance that we used throughout the course of the pandemic that we're using for helping institutions prepare for wildfire, and so implications for both. Also, we want to consider different methods, right, for being able to measure directly. We do a whole 2-day course on this, so look for those upcoming announcements if you want to get into the nitty-gritty of how to do that. We're going to kind of just take a real cursory level at that, but thinking in terms of filtration, dilution, ventilation, how do those all work together? And then we're going to take a look at a particular case study and see, well, if we've got, if we can measure, if we can quantify our dilution, if we can quantify removal through HEPA filters, if we can quantify removal through MERV filters, does the benefit of each of those individual pieces actually add up to what we would expect it to? And this is important, right? For thinking, well, if we want to make sure we've got at least 3 air changes locally in an office space, how do you know you're getting that, right? And so tools for being able to assess that. So my very first industrial hygiene professor, Mark Mikas, drew a box for me a little over a dozen years ago, and basically said, you got stuff coming in, you got stuff going out, and that image has stuck. And so essentially, in terms of air changes per hour, you're talking about air coming in, air going out. In this case, we're just thinking single pass air. Whatever comes in is equal to what's going out. And if you've got 100 CFM, cubic feet per minute of air, that works out to be about 6 air changes per hour in a 1,000 cubic foot room, of course, not considering the volume of stuff that might be in that space. How would you measure that? Well, you could put a bolometer up to a register and get direct airflow, so you would know what your CFM, and what we're doing here is actually measuring local air exchange, not necessarily what would be representative of a laboratory environment where you have air going in and air going out, single pass, as I mentioned. But this would be rather more typical of our building spaces, office spaces, where you have air that moves through the building, works its way back through an air handler. It's diluted by a percentage or a proportion of outside air to make sure it's fresh and not stale, and flushing the CO2 out of the space. And so it's hard to visualize what this looks like, but actually I have a video that I make no claims about this particular filter. They just put out this video that I think visualizes, and I've been looking for something better to describe it, because what he's doing is, I think, a little crazy, but you'll see. What am I talking about here? Essentially, they have this chamber.
Pairs with what we're about to release.
Some tear gas into this space.
David, we're having trouble hearing you over the video audio.
Sorry about that. So they release some tear gas into this chamber. He's breathing through the exhaust from the HEPA filter, right? So it's saying, oh, look how clean our HEPA filter is. Any HEPA filter would theoretically do this if it had the right cartridges, right? Because they probably also have a carbon filter here. But the important piece that I want to show here is after they've got it filled up, what it looks like in a time lapse.
Frank breathing the clean air stream coming directly from the Health Pro Plus. The IQ Air Health Pro Plus is clearing the room.
So if you could visualize the airborne contaminants, whatever that might be, whether it's carbon dioxide, which of course we can't see, wildfire smoke, which if it's PM1, PM2.5, also we're not going to be able to see, or formaldehyde, or whatever the airborne contaminant is, visually, this is what's happening when you're effectively removing it, if your measurements are effective at removing. Oops. So what is good then in terms of air changes? Well, Harvard came out years ago and said, all right, at a bare minimum, we want 3 air changes per hour. This was, for schools, but also, actually, I take that back. For schools, they recommend a little bit higher. For office spaces, a minimum of 3. Well, where in the world did that come from? Oh, and I forgot to mention too, if you have some scratch paper handy and a pen or pencil, we're going to grind out a little bit of math. It's not going to be complicated. but I can't lead you through this stuff without giving you a chance to get hands-on with some of these calculations that seem scary initially, but hopefully are not so bad. All right, so
David, it looks like we're still on the video. I'm not sure if you've gone back to your slides already.
I did. Let me, sorry about that.
Thank you.
Thank you. All right, so here we are. Everybody see that? Or Michelle?
Yep. Yes. Thank you.
Okay, so this was our playbook. This is a fairly long document, about 150 pages. You do not need to read everything. It's not a novel. It's I recommend diving into various sections of it. They have this really intimidating calculator that essentially Harvard's and CU Boulder said, nah, we're going to simplify this a little bit more for schools. And I simplified this for me even more, just basically, and this is coming right out of ASHRAE 62.1. This isn't new stuff that they're inventing. This is just applying what we've already known. And what do I mean by simplifying even more? Well, essentially, for a classroom, for example, 5 to 8-year-olds, many of us are parents, standard occupancy is about 25. Okay. And what does a 25 occupant classroom look like? Well, it might look like something like this. I know it's also a concern of ours as new variants emerge. How's that going to look? And all of you parents, I think it's your technical expertise and background getting involved with your school to find out what they're doing for ventilation. They're all going to be mad at me now for suggesting that. The schools, that is. No, I think for the most part, schools have been pretty receptive to sharing this information. But essentially, going back to ASHRAE, classroom of 25, this is the key data you need, right? CFM per person and the CFM per square foot. And so this works out to be, we'll do the math. Let's see. Let's go back. All right, so we have 25 people in this classroom. We need 10 CFM. Most of you could probably do this in your head, but I encourage you to write it down just so you can visualize it, burn it into your kinesthetic motor memory. So 25 times 10, we need 250 CFM per person. We have 1,000 square foot classroom. ASHRAE says 0.12 CFM per square foot. So 1,000 times 0.12 works out to be 120. 120 plus 250 is, survey says, 350. And that 350 CFM is specifically, or at least prior to COVID, is talking about outside air coming in, right? Because that's the only thing that's flushing gases and vapors. There's no filter that's going to remove that. We know, of course, MERV filters, HEPA filters also remove aerosol, right, which is a particulate. But 62.1, it was just based off of outdoor air, right? Outdoor air exchange, how much is flushing out? So at a minimum, we're talking about close to 15 CFM per person and around, what, 2.8 air changes per hour. That's weird. That seems awfully familiar. How do they get to 2.8 air changes per hour? Well, it's simple formula, CFM times 60 minutes divided by the room volume. And so if we recall, we had 370 CFM that's required per ASHRAE. And of the 25 people, right, we just take 370, divide it by 25. You could do this on your phone calculator, and you're 14.8 CFM per person at a minimum, right? This is just minimum ventilation for indoor air quality. I'm not saying this is protective. Those are two very different things. But what I am saying is that many institutions weren't even meeting the minimum. And in those institutions where they were, we just didn't see transmission at the level we saw elsewhere. And what does 2.8 air changes per hour look like? Well, it might look something like this. What are we looking at here? We're looking at a graph of carbon dioxide where we filled up the space to about 2,700 parts per million. of carbon dioxide, which in an underventilated classroom, you could expect to see something that high. And then we tested out a condition. I think in this case, we were looking at windows. And so we had removal, right? You see the concentration build up, we open the windows and we watched it all flush right back out. It definitely does not look like this, right? So even without doing any calculations, if you're just looking at the data, the graph, this can tell you a lot. If we have time for it, I've got a couple more examples towards the end. We'll see how I'm doing for time. Usually not very good. I'm usually behind. But anyway, so I don't know if you all remember seeing this maybe a year and a half ago where they said, oh, there's no difference between 3 feet and 6 feet. Well, that's not saying 3 feet is protective or 6 feet is protective. That's just saying we're not seeing any difference in terms of transmission rates. We're still seeing transmission, but that's not the mediator, right? That's not the thing, the difference maker. And if you look into their study and you try to figure out, well, what did they look at ventilation at all? Well, this is actually just saying that they didn't see any difference between physical distancing, even though case rates were similar amongst staff in the community, blah, blah, blah. But with respect to ventilation, what they said was it was highly heterogeneous. What does that mean? Highly heterogeneous. It means it was all over the map and they didn't know how to track it, right? There was no efficient way to really document, well, what did the ventilation look like in that space? And we've done this now for, I want to say, a dozen or so different schools. We've done this for about 200 office buildings. It can be done, right? It takes time, it takes people, it takes resources, but it can be done. What they found in this Massachusetts state study, was they used a combination of opening windows, HEPA filters, HVAC upgrades, move class outdoors. So different things at different times. And what I would very much love to be able to do is be able to come up with a systematic, easily quantifiable way of measuring a space, just like you would measure the temperature. Before you step outside, you look at the weather and go, is it going to be raining today? Is it going to be 90 degrees? You make adjustments. You accommodate for that. So how do we quantify that? Again, very intimidating looking graph. I encourage you to dive into this if this is something you nerd out on, because you can pull it apart. You can tease these little variables apart. But for me, again, just like wanting to simplify things, this is ASHRAE's infographic here. I had to put it in terms that were simpler for me, right? And sometimes describing it to somebody, whether it's your colleagues, whether it's your clients, whether it's your children, helps us to understand it, right? We all know that. We learn best when we teach something. And so borrowing from that really complicated looking ASHRAE formula, which thinks of everything, I just said, let's keep it simple. We need to know the amount of outside air. We need to know the amount of return air, what the percent of that MERV filter is, or rather what the MERV rating is, and we can estimate a percent of removal. And then you're going to put HEPA filters in, or we could ask the question, how many HEPA filters do they need in order to get to a certain amount of air change per hour they were looking for, right? How do we bridge that gap? And the vast majority of the time, the legs, if we lift with our legs, right? We don't lift with our back. The legs in this case is the HVAC, right? It is the ventilation. These are school environments. Unless they're using some space that wasn't really designed for a classroom, classrooms are generally designed to provide ample ventilation. They just need to use them. They need to change out the filters. They need to, make sure that they're running. That was probably the biggest problem we ran into over the past 2 years was they're on, but they're in fan auto mode. So they're only running when the temperature drops either too low or too high within that dead band, right? Where it's like, oh, temperature's perfect. We don't need to ventilate. Energy saving feature. I get it. It's good for saving energy. It's good for protecting the environment from climate change. We're going to need better strategies than shortchanging our ventilation, I feel. As I mentioned, this is something that's also going to be protective for wildfire smoke in the classroom environment, in the office environment, And so knowing your ventilation in advance can help you estimate how protective you're going to be, your space is going to be, your organization, your office, wherever the case may be. And this was, I think back in 2019, we had a dear friend who was very close to one of the fires up in Northern California, had an infant on the way. We just put together, $40 setup, MERV filter that you can buy at any, local hardware store, put it on the back of a $20 fan, and we saw close to 4 air changes per hour reduction in PM 2.5. So, I mean, seeing is believing sometimes. And if you have tools to be able to do this, do your own assessments, it really does help to sink those concepts in. So what is this based off of, right? So we're thinking about wildfire smoke. Well, each MERV rating has a percent that it is expected to remove of various size fractions, right? Your smallest fraction, your smallest particles are in the E1 category. Next up is in that E2, followed by that E3 category. And of course, as you get bigger, that MERV filter is going to do a better job of removing particulate. But you can also get this information right on the back of a MERV filter. It says right there what is its percent efficiency within each of those bands. So PM 2.5, as you can see, is right there, smack dab in the middle, which we know PM 2.5 is not just right at that point. It's a little bit of the big stuff. It's a little bit of the small stuff. It's basically 50% of the mass is coming from PM 2.5 or less. So it could be, you get some big particles that are floating in there as well. All right, so the meat and potatoes of what I want to talk about. Maybe I'll just pause really quickly and see if there's any questions. Show the formula and defined terms. Sorry about that. I can go back to that and let's see. All right. Moving on. I will go back to that if I have time to do that, and I apologize if I race through that. All right, here we go. So this was a classroom that had some atypical ventilation. You couldn't just put a bolometer up there. There are no bolometers. What you see there on the wall, those metal things, are just louvers, passive louvers, just allowing that pressure to move out of the space. You can see in the back there, you've got these unusual supplies. This system was 100% single pass, also unusual in that they were not recirculating any air, just 100% coming in, 100% going out. So that's why they had those louvers. They've got all these windows around the space. Up at the top, you can see there. They also had these ceiling fans, which aided in mixing. So unusual space that warranted taking a more unusual approach to assessing ventilation. Is about 60,000 cubic feet. So again, atypical classroom size, but this could all be applied into a smaller scale as well. We used just a straight up $40 Vicks humidifier with salt water, basically the salinity of ocean water. I want to say it's about 30 grams per liter, and made a salt spray. And as it builds up over time, we had 2 of these set up in this 60,000 cubic foot space. You could start to see that hazy look that you get when you go to the ocean. And we're like, okay, we're getting pretty close here. We could have opted for this super fancy polydisperse aerosol generator, but I kind of was attached to the idea of not spending $20,000. I don't know if that's exactly what it costs. I can't remember now, but it was more than $40. I'll tell you that much. There it is. And it's not just water, right? There's salt spray in there, and that fan behind it helps to dry it out. This is why early on in the pandemic, they said, oh, don't put fans facing people's mouths, because if you exhale and you're talking and sneezing and laughing and coughing, that aerosol, as it dries, well, it gets smaller. The smaller it gets, it stays airborne longer. So that's essentially what we were trying to create in that space, right? We wanted that sodium chloride aerosol to stay airborne longer because we wanted to measure it. We wanted to test out different different conditions. Well, we also had, there was another lab, it was a Taylor lab that was there also doing their own studies. They got way fancier equipment than me. I was kind of geeking out on their stuff. But here we go. So we also had access to the building management system, and they provided data on the different VAVs. So variable air velocity are the two units that provided CFM, cubic feet per minute. They provided airflow. The supply was moving through a MERV 13. So we were getting from each of these around 600 CFM a piece, is what the building management system said. This is a fairly new building. Most of these sensors are pretty calibrated. When we've put up our bolometer for these new buildings, and the building management has a system where they can adjust the flow points, they're usually pretty close. Some of the older buildings where there's been a lot of modifications, I don't know that those are as trustworthy. They tend to be off, and it's partly due to the fact that just modifications have been made over the years, which is why it's so valuable to measure in the space you're questioning, right? You're going to have a conference of people in this room. Well, let's measure in that room, right? Let's not look at what the computer screen tells us, because that might not be accurate anymore. They often go out of calibration. They're not maintained. But this one was brand new, fairly calibrated, so we trusted that it would be fairly accurate. We also deployed, we wanted to test out a number of HEPA filters. These are large units. These were smaller units, so we kind of combined those in the space. As I mentioned, the Taylor lab, they were also testing out one of their units that they built in Jacobs Hall. And so this was basically to see how, you know, if they could get removal from MERV 13, which I said, yeah, absolutely, I've seen it, right? This earlier study that I looked at wildfire smoke, I'm like, oh my God, look at that. Let's just being removed so efficiently. I didn't expect that. And then we threw the kitchen sink at it, right? We had both the HVAC on, HEPA filters, MERV filters, ceiling fans going. So we wanted to test all that. And so my question was, I mean, this wasn't the main reason we were doing it, but another question I developed after the fact was, do they all add up? If you expect 400 CFM, or you expect 600 CFM from either supply air or filtered air, do you get that? Do they cancel each other out somewhat? Are they additive, right? So that's what we're looking at today. So we always do baseline tests, fill it up with aerosol, fill it up with CO2, two readily available airborne contaminants, and we kept the doors shut, no HEPA filters, windows were closed, and here's what we had, right? So there was some passive diffusion. This is carbon dioxide now, so you could see kind of slowly building up over a span of about 30 minutes to a half an hour, and then plateaus. We say, okay, let's get out of here. We let it run its course for another 30, 40 minutes or so, and we get a nice gradual decline. It's just passively making its way out through the cracks. It's not a tight seal, right? So purportedly nothing was on. We did have some issues later, we learned, where, oh, sorry, we didn't mean to have the ventilation on, but it was on when you said you didn't want it on. So there were some communication challenges that we were wrestling with. Aerosol, PM 2.5, not too different. It's a little bit more than carbon dioxide, right? But we would expect that. Why would we expect that? Well, aerosol is not a gas, even though really small aerosol, PM 2.5, PM1, behaves like a gas. It's still a particle, and it will still deposit on surfaces. It will still fall out of suspension due to gravity. So we're going to have more modes of removal for this particular aerosol. So that was to be expected. Next up, we then said, all right, let's fill it up again. And we're going to test out the ventilation. We want to know, well, how much removal do we get from the HVAC? And we had windows open. We had the ceiling fans going to facilitate mixing. So we make sure we got a nice stable concentration. And what do you know? We calculate this out, we get 1.1 air changes per hour. 1.1. Interesting. So we had estimated about 1200 CFM. So you can do this calculation with me too. So bust out your calculators. All right, so we do 1.1, so the number of air changes, and the volume, we'll call it 64,000 cubic feet. So we take 1.1, multiply it times 64,000. So that's our cubic feet per hour. That's our Q. If we divide that by 60 minutes, oh, interesting. Should all get 1173. So this method, right, looking at CO2 at the benefit of the HVAC, where we're estimating, where the system is telling us we should be getting about 600 CFM per unit. There's 2 units, so 1200 CFM. When we test removal of carbon dioxide, we get about 1200 CFM back calculated, right? So we're going the other direction. We're solving for CFM by first solving for air changes per hour, the rate of decay, the expected rate of decay from a measurable airborne contaminant. Any questions about that? I know I said I wouldn't ask if anybody had questions because we would take forever to get through it, but I know this is an important point, so I want to just make sure. And I see there's, all right, there we go. With aerosol, again, we get slightly higher removal rates, possibly with more airflow, we're getting more impaction, which likely from a respiratory aerosol, transmissible disease, we would also expect some additional removal. So if we're estimating we got 1.1 air changes in this space, we probably have something closer to 1.4 when we're talking about respiratory aerosol, especially because it's polydispersed, right? You got big stuff floating in the air, mixing around with small stuff and everything in between. We then decided, well, okay, that's not a lot. It wasn't designed. It was not designed as a hospital facility. It wasn't designed, during a pandemic. This space was designed pre-pandemic. So they said, okay, well, we want to hold classes in here. We got to make sure that we're doing everything we can to keep everybody safe from a ventilation standpoint. They're going to have all the other mitigation measures in place, right? But we don't want to create an under-ventilated environment. So we threw everything at it. Let's test everything out, right? HEPA filters, remember we had 4. We had 2 of these bare air units that were from the Taylor lab. And well, what did we get? Not surprisingly, we boosted substantially our air change per hour. We couldn't obviously do this with carbon dioxide at this point because what we're measuring is the benefit of filtration, which of course carbon dioxide is just going to move right through that MERV filter. It's going to pass right through that HEPA filter. There's no filter, to my knowledge, that will remove carbon dioxide, right? The only thing that's going to remove carbon dioxide is fresh air, right? Is some other gas. But an aerosol, sodium chloride particles that if you live near the coast, corrode your car and other stuff that you have that's metal, perhaps, is what we're measuring, because that does get removed by MERV. That does get removed by HEPA filters. Well, then we said, well, okay, let's take out the benefit of the bare air units, which again is just a MERV 13 filter. So 220 by 20 by 1 inch MERV 13 filters. We remove those out of the equation. We unplug them. We're not going to test those. We're going to test this separate and see what happens. No, it drops, as we would expect, right? It's not getting as efficient of removal. Let's go back here. Just like, whoa, look at that slip and slide. That's great, right? In terms of removal. And again, calculating out, we get 3 air changes per hour. This one, not quite as dramatic, not quite as steep, still an improvement upon the HVAC alone. And of course, this has implications as well for wildfire particulate if we're dealing with PM 2.5 inside a space. This is what we would expect to see in terms of removal with respect to wildfire smoke as well, right? It should be removed by the same mechanism. HEPA filter doesn't care if you're sodium chloride or you are PM 2.5 from a wildfire, it's going to remove you just the same. But to answer, to get at our question of, well, does it add up? Does that actually add up? Well, we separated it out, right? We wanted to test HVAC bare air. So we're removing the HEPA filters from the equation. So the last test, we removed the MERV 13 bare air units. Now we're putting them back and taking the HEPA filters out. What happens now? What do you think happens? We know the HEPA filters, we got about 0.4 extra air change per hour when we had these units in there. And we had 2.6 as compared to 1.4. So we had about 1.4 higher. You don't have to memorize all these, because I'll give it to you lined up in a second. But we had about 1.4 more with the HEPA filters and about 0.4 more with these units, which is not surprising because HEPA filters are going to remove more, but that doesn't mean that these aren't removing nothing. They're definitely removing something. So we got about 1.8. So we got about a 0.4 bump. Hold on a second. That's interesting. We go back to this 3.0 air changes per hour. That's with the kitchen sink, right? Everything was thrown in there. We take it out. We drop by 0.4. We put it back in, removing the HEPAs. And again, it's that 0.4 difference from just HVAC alone. So, well, does it add up? So again, our straight up HVAC, there's a graph, 1.4 air changes per hour. Throw in the MERV 13 bare air units, we bump it up by 0.4 air changes per hour. We've got the kitchen sink at 3 air changes per hour, right? What we would expect of the biggest removal rate. So we remove the bare air from the kitchen sink, and that equals 2.6. What? It wasn't all so clean. Another way of slicing this, and stop me if you need me to go back. Another way of slicing this was looking at the air change per hour, what we estimated, right? So we were given specs from the HEPA filter. All right, this one will move 400, this one will move 75, this one will move 400, but it's a MERV filter, so it's going to be a % of 2.5. So we estimated, we added it up. We used that ASHRAE formula. We know our outside air, we got 1200 coming in. We know our HEPA filtered air, we know our MERV filtered air. What do we actually see inside? So in our primary test, our HVAC test, it was pretty close, right? So what we estimated we would get for the benefit of HVAC was right around what we saw in terms of CO2. And then we were looking at, I don't know why I chose PM1 here. I would go, actually, I think it wasn't much different than PM 2.5. That's why. And this was also because my academic advisor, Kathy Hammond, said to me years ago when I told her I was surprised when I was doing some exposure monitoring in the field for wildfire smoke. I said, I changed out the impactor from 2.5 to 1. I said, and the number didn't change at all. She's like, well, yeah, of course. I'm like, what do you mean, of course? What did I miss? I missed that lecture. Can you give it to me again? And she basically said, when you're that far away from a fire, most of it is going to be, and I'm paraphrasing what Kathy said here. So if I'm wrong, Kathy, I apologize. So what she was saying is most of what you are going to find 2 hours from that space is going to be the smallest fraction, right? It makes sense that the smallest stuff is going to stay airborne the longest. It's going to travel the furthest. And so what I was finding in that early stage in my career where we were asked to go around campus and go monitor PM 2.5 was we were really looking at PM 1. And I think that's why I said, okay, I would just want to be more protective here. We're going to look at PM 1. So it increased a little bit. It got slightly better when you went to PM 2.5, right? Because the particles are bigger and you're going to stop more of them in the MERV filters. With HEPAs, they're going to take it all out. They don't care. But in the MERV, it's probably more ability for them to pass through. This is where we overestimated, right? We estimated we would have gotten somewhere close to 4 air changes per hour. And we didn't, right? What we measured empirically, looking at PM1, was only 3, right? Going back to that really big graph, that graph with the really big decay, we only got 3. So what's happening here? We're not sure. It could be that there were issues with ventilation and stuff got turned off when it was supposed to be running. It could be that the units were not delivering what we thought they were. It could be that it cancels each other out, right? It's not necessarily additive, right? That throwing more HEPA filters doesn't provide the same benefit as just having one system that's going to deliver the required amount of ventilation, which I think also has implications for climate change. As we still ask those questions, do we put HEPA filters in? Do we not? It's just putting more electricity on the system. Again, thinking about the legs of those buildings, the ventilation is working right, that should be providing the vast majority of the ventilation that's needed. It's rare where we recommend the use of additional HEPA filters. Plenty of cases, of course, where people have put them in, but you know, it's kind of some exceptions where we recommend it. Still the same difference here, about 0.9. This I cannot explain. I don't understand why we estimated less, but we actually got more removal. Each one of these took hours, right? So it's quite a laborious process to set this up, to run the test, to analyze the data. And this has actually inspired another round of testing where we're going to be working with a more controlled environment in a roughly 10,000 cubic foot classroom. So hopefully by this time next year, I'll have the results of that study to share with you all, if you're not totally turned off by ventilation at that point. But again, I think I encourage you to do your own testing, and this applies as well to other environments too, right?
David, can I
Yeah.
interrupt you for a second? On that last slide, can you share what were the testing conditions for 1 through 5?
Yeah, sorry
Are they all
about
the
that.
same?
So 1 was our baseline. 1 was just basically everything was off. No, just passive removal in the system. Test 2 was, all right, let's crank the HVAC on. Let's get the HVAC going, get those fans running, and no HEPA filters, no MERV filters inside that space. Test 3 was the kitchen sink. Let's just throw everything at it, right? So we got our MERV filters, we got our HEPA filters, we got our HVAC going, ceiling fans, it was cranking. And then we decided for test 4, well, let's leave the HEPA filters in place and take out the bare air units that were providing MERV filtration. And then we reversed it for test 5. We pulled out the HEPAs and we switched them off, and we put the bare air units back in.
Great, thank you so much.
Sure, thank you for that question. And so, is it also possible that, who knows, something to do with the velocity, there was more impaction, some other mechanism that was removing aerosol in a way that I'm not an aerosol scientist. I'm just a nerd when it comes to exposure monitoring equipment and measuring this stuff. And I don't think you have to be an aerosol scientist to get a lot of really valuable information out of this data that you can collect. As I mentioned, we do a 2-day course to kind of give you some of those basics, but you can talk to the manufacturer's reps, to the vendors, and they should be able to give you. And nowadays too, there's so much cheap equipment out there, right? You've got those little portable CO2 sensors. You've got the little portable PM 2.5 sensors. You can get that same data. It's a little more, you don't get the fancy graphs the same way. Well, I take that back, you do with some of them, but it depends on what you're used to, I guess. So as I mentioned, this is appropriate or applicable understanding how ventilation works for other spaces where you may be dealing with airborne contaminants, right? I was dealing with formaldehyde exposure monitoring challenge situation. I said, hey, can I take a look at your mechanical drawings for this space? We identified where the air handlers were for this particular lab. And we said, all right, we want to get up on the roof and go take a look at this, because we were told, oh yeah, we're maximizing outdoor air. How many times I've been told that? How many times I've actually gone up on the roof and looked at the air handler and I'm like, that's the opposite of maximization. You are minimizing outdoor air. This has been the paradigm, right? For decades. Because why? Because it reduces the amount of air you have to condition. It's cheaper, keeps people more comfortable from a temperature standpoint, humidity standpoint. It's less energy intensive. There's a lot of good reasons. It was our Achilles heel. It is our Achilles heel, dealing with aerosol transmissible diseases, dealing with airborne contaminants. And so we got up on the roof, looked at the two air handlers that are responsible for supplying that lab where we were having the formaldehyde issue. And there's the air intake right there. Lo and behold, the maximized damper to the outside air was completely shut. I said, can you get somebody to open it up? It said, I'm going to need special authorization and the football code to do that. They had to go highest level up in the facilities, get the authorization, get the approval. And when did it happen? You guessed it, right around in between 1400 and 1430. Yep, that line is where they opened up, about 2:45 in the afternoon, or not, it wasn't 2:45. So it was about, I guess, I can't read military time, as you can tell. So around 2:15, opened it up, boom, saw this immediate reduction of carbon dioxide. We weren't measuring, we weren't tracking formaldehyde, we don't have a real-time data logger the same way we do for CO2. So again, CO2 is just a great surrogate for thinking about airborne contaminants, thinking about how ventilation interacts with the space, especially if you're dealing with vapors and gases. But again, there are other tools to be able to do that. And then, as I mentioned, you don't need to be able to do these types of calculations to get valuable data out of this. This is another classroom environment where they had CO2 monitors installed, where they were basically running with double the number of students for the size of the space. And you see these peaks every, happening basically when they were holding classes in there. It's like, why do we have CO2 up around 1200 plus? We shouldn't be, right? You can see background is in the 400 to 500 range there. And we didn't need to do any calculations to go, oh, look at that. We've got some spikes in CO2. What's going on in there? Oh, well, we're overcrowded in our classrooms. Okay, we need to find you another classroom then. Or we got to do something else. Same thing here. Look up close at this particular graph. This was just me in a class where I held up the CO2 monitor to my face, said, okay, look at where it's at right now. It's spiked at 1,000 because I exhale a lot of carbon dioxide. And then over time in my garage office, it gradually built up. And then just before we went to lunch, I think it was just afternoon, I said, hey, look at this. This is this is where it's at right now. It's gradually built up a little bit higher. And then I opened up the windows, left the garage, and you see this massive reduction. And then it goes back to background and never comes back up again. So really powerful data that I didn't have to do any calculations on, right? You could just visually see what's happening in that space. This is another one where I went to a concert early on when this is before, I think it was just before Omicron or I can't remember exactly when, but I'm like, I'm taking my CO2 monitor, my portable one, kept it in my pocket. That early spike had to step into the men's room. And then the CO2 felt relatively controlled over the course of the evening. And then it dropped again as we went outside. Had I seen these massive spikes or increases, then I've been like, ooh, I better isolate for a couple days until I make sure I'm not, or quarantine rather, make sure I'm not positive here. And just to kind of point out here, this all assumes a well-mixed room. Not all spaces are well-mixed. This is where, if you want to get really in depth with this, ASHRAE has this, which is baked into their ASHRAE preparedness document that you'll have referenced in the presentation. But basically saying like, look, not all systems are created equal. If they're not well-mixed, you don't expect the same removal that you would get from a well-mixed system. What do we mean by not well-mixed? Well, if you got the supply right next to the return, air isn't really moving through that space. It's just coming in, going right back out. It short circuits. This is kind of hard to visualize here too, but right in the center, you've got this kitchen space that has no supply or return. So we can't really treat that mathematically as equal to those other office spaces, right? Or that conference room where you've got a dedicated supply, a dedicated exhaust or return. So you're going to facilitate more even mixing and by extension, more efficient removal of airborne contaminants. If you're intimidated by mechanical drawings, I would encourage you to, I don't know if they're offering it currently, but I saw it, I looked up the other day, shout out, I forget his name, but this really nice gentleman came out to our office and taught us a blueprint reading course and tailored it to us. So if you are a nerd in ventilation like me, and you want to learn more about reading mechanical drawings, I highly would encourage you to check out one of these courses. It was like a 2-day or a full day, I can't remember exactly, but it was really valuable, really insightful, and it will hopefully get you less intimidated about diving into these mechanical drawings and starting to ask some of these valuable questions in thinking about your spaces and being resilient for future aerosol transmissible diseases, future wildfires, thinking about the environment and how do we get the greatest bang for our buck in terms of ventilation without costing ourselves long-term in terms of energy and climate. And with that, I will gladly open it up for questions. Thank you all for your time and attention and patience with me.
Awesome. Thank you so much for your presentation. If you have questions, please do enter them into the online Q&A box. And the Q&A is a little bit easier for me to keep track of what has been answered and not answered so far. So first off, can you review how you get your decay graph to calculated ACH?
Yes, I go into detail there in our online class. And there are a couple different versions of this formula, but it's basically, you can do it right now. If you've got an Android, it's a little different if you have an Apple. So if you've got an Android, you basically, I'm blurring my background so you won't be able to see it. Okay, I'll just talk you through it. So basically you take your starting concentration, your ending concentration, and there's some debate about whether or not you subtract out background if you're dealing with carbon dioxide. And then you multiply that times 60 minutes, divide that by the total time it took to get from your starting concentration to your ending concentration. And voila, you have an air change per hour concentration number. I know that's really brief. And if you email me, I can send you more details on that, and also some slides on how to just calculate that, as well as to cover the controversy about using background or not to use background. I prefer a simpler version just so that people can get data. And it tends to be a little more conservative, tends to be a little more protective when you calculate it without the background in there. So it's just natural log in parentheses, concentration 1, your starting concentration divided by your ending concentration, multiply that times 60 minutes and divide it by your time that it took to get from C1 to C2. Sorry, and that was probably the worst way to share that information.
Well, thank you.
My whiteboard, my imaginary whiteboard.
And perhaps for those online, we can put up an equations cheat sheet on the
Yes.
webinar page after the event. So if you wanted to go back and reference some of the equations, we can put up a little cheat sheet for you. Great, thank you. And that also, I guess, just to kind of revisit the formula and defined terms, we had a question about that, David. I know you saw earlier. That was actually before you showed the slide with all of the defined terms, but we'll make a point to have the formula and defined terms on the cheat sheet we'll share with all of you as well. We also have a thank you very much for this valuable information comment, and another comment that says, great job, woohoo, followed by a question. How many ACH is needed for infection control?
That is a great question. So if you were, the short answer is we don't know. But in a hospital environment, if someone came in with a known aerosol transmissible disease, COVID, tuberculosis, anything else, they would at a minimum be required to provide 12 air changes per hour. So what does that mean, 12? It means basically you're getting the benefit of 3 air changes in about 15 minutes. Well, we have this 15 minutes of, within somebody's 6-foot bubble. Again, there's arguments that that's arbitrary and based on outdated science. I'm not an expert on that, but what I do know is that at a minimum, those spaces where you have an airborne infection isolation unit in a correctional facility, got to have 12 air changes per hour at a minimum. If you are dealing with an asbestos containment facility, I believe it's 6 air changes per hour, maybe it's also 12. But kind of in that 6 to 12 range is generally what you see in a hospital environment, whether you're supposed to anyway, in a nursing, where you would be seeing patients or whatnot.
Great, thank you, thank you. And what mixing factor did you assume in your estimates, and what mixing factor did you really get?
Yeah, that we didn't get into the mixing factor, but that could be why we saw discrepancies from what we were expecting and what we didn't see, right? So we were expecting 4 air changes per hour because we're throwing everything at it, and we only got 3. What's going on here? So maybe it wasn't as well mixed as we thought. We thought strategically, we positioned the bare air units opposing to create somewhat of a vortex. We positioned the large HEPAs towards the back of the room with the highest portion of the ceiling, and the fans were kind of in the middle. So we were assuming going up, coming back down, swirling in a vortex. So we assumed 1, right? But that was probably more due to the fact that it's just easier to simplify than us knowing how to apply that. That also, the mixing factors is not something that I have expertise in, and I think it goes back a little bit to the art and science of industrial hygiene. So I'm more of an artist, I think, in that regard, but I'm sure there are some engineers out there that would say, oh, this is how you would actually accurately quantify that mixing factor, and that there is some basis for how they came up with those numbers.
Thank you. And someone asked for a continuing on the air mixing a bit more. Is more mixing better? Can you share any background on, is it better to have more mixing, less mixing? If you don't know what the ventilation information is there a way to estimate what the mixing factor is?
Yeah, so I think most modern buildings are designed to be well mixed. You're going to find spaces that are not, but in general, you want your supplies evenly distributed throughout the space, and it sends out air in a diffuse, cascading way. Think of it as a gentle rain, right? That really nourishes the soil rather than a torrential downpour. So gentle, even mixing, and we do generally find this. So if we've got multiple monitors staged throughout a place, you see the levels equilibrate fairly quickly in a modern, what we would assume to be well mixed space based on the distribution of supplies and return. You don't want, of course, like a fan right next to somebody's face. That's not ideal, especially if we're dealing with aerosol transmissible diseases and people are no longer masking. But that sort of gentle overall mixing does help facilitate with dilution and eventual removal as well. So generally it's considered a good thing.
Great. And what would you predict, if any, on the ACH calculations if you had students occupying and moving around? For example, if you were getting eddy currents in a space?
Yeah, so I should have started with that there was nobody in the space when we're doing those measurements. So it's kind of looking at the space in isolation. And of course, if you have people moving around, you're going to facilitate greater mixing. Air molecules are constantly bouncing off of one another anyway. So it would increase the mixing factor for sure. How much? I don't know how to quantify that, but also another part of that question too. Oh, right. So if you're looking at CO2 and you have students in that space, you're not going to see as dramatic a reduction of carbon dioxide, right? It's going to stay kind of, it won't be, because you're still generating more carbon dioxide as you're removing it from the system. You may see removal, but you may also be biasing that CO2 level up, in which case you're shrinking your air change per hour number, what you would conclude at the end of that. I don't know if that made sense or if I just made you confused.
Another question, are we able to apply these general concepts to office buildings?
Yeah, we have. And I think, this goes back to the discussion about, well, we need ventilation. Well, how much? How much ventilation do we need? Well, ASHRAE makes recommendations. If we're in California, Title 24 has requirements for minimum amounts of outside air. And so if we know the percent of outside air that's coming into that building, and oftentimes newer buildings are sophisticated enough to give us those details and generally are trustworthy enough numbers, then we can determine, are we at least meeting minimum requirements? If we've got a bolometer up there measuring airflow coming into the space, you can hire companies to come in and do this. When I was at UC Davis as an industrial hygienist, I would just pick up the phone and ask one of the HVAC techs, hey, can you go get some numbers in this space? I'm having some issues that we're dealing with, whether it's in an office space and they've got allergies, or it's in a lab space and they want to store liquid nitrogen. Absolutely, both these concepts, air change per hour, how much of that is outside air, because it's not just quantity, right? It's quality and quality. It's kind of like, well, we've got a HEPA filter provides 99.97%. It's like, well, if you, not to call out the French Laundry, I've never eaten there before, I would love to, but I think they serve really small portions. Amazing food, but really, really small. It's like a HEPA filter that's 99.97%, gives you really high quality air, but it may only be a small portion. So it's good quality, but if you're catering for a lot of people in an office space, in a classroom, in a lab environment, you got to make sure you have the quantity as well. So it's looking at both of those factors, quality and quantity, and in which case that it definitely applies to both office environments, industrial environments, laboratory environments.
Great, thank you. Well, we are wrapping up here. I do have one final question. Do you use any visual indicator like smoke tubes?
I do. Sometimes it's helpful. For example, when we were doing a lab inspection recently, if they weren't certain about whether or not the space was under negative ventilation, not smoke tubes. I don't use smoke tubes. I use this other, I think it was like a toy before, and then the HVAC industry was like, oh, we could market this as an HVAC tool and charge 10 times more. But my industrial hygiene mentor, Phil Maynard, used to use the smoke wizard. We would call it the bong, but it was like marketed to kids as a toy called the smoke wizard. You push it and it was like glycerol or something like that, and so it would emit an aerosol that you could visualize, watch the smoke qualitatively being drawn into a fume hood, being sucked into a door if it's a lab environment, hold it up to a register. Oh, that's a supply. Oh, it's going into that register there. Oh, that's a return. It can be helpful. I try to stay away from the really harsh smoke tubes, but for ASHRAE testing where they're commissioning a fume hood, they will use quite a bit of smoke to make sure that it's got good capture of velocity. And they use like a whole smoke machine setup. I've not personally worked with those, but that's another possible tool you could to visualize it. And that's actually a good idea for maybe creating our own video to visualize what removal looks like. So thank you for that idea.
Awesome. And that actually reminds me, if you could send the link for the video. We did have a request for somebody who wanted to rewatch that video.
Sure, I'll include that in the presentation for sure.
Thank you. Well, thank you all so much for being here. A special thank you to you, David, for this presentation. For more information about upcoming webinars, upcoming events, and ventilation trainings, you can visit us at coeh at berkeley.edu/about-ce. I've also put a link to the evaluation in the chat today, and you'll get an email automated from Zoom tomorrow at noon Pacific time with that evaluation as well. So thank you all for being here, and I hope you have a wonderful day.
Thanks, everyone. Take care.